All right, guys, so 3.5. This is the last section we're going to cover before our next test. So I'm pretty sure you guys clarified for me that we don't have school Monday, which I forgot about. So, so we're going to do this today. Wednesday, we'll do our review activity, and then the following Monday, you'll take your test. So you got a lot of time to study. Do not wait for 5 days and not study, okay, and then wait another week, okay? I'm telling you, it doesn't work. That would be a very bad idea. Question?
Are you going to give us like a review test?
No, I was going to do the review activity, plus your test review is on the My Math Lab. Yeah.
Is it printable, do you think?
It should be. It should be printable. Yeah. Like half the people still haven't noticed that in the first test review that I did, like on the actual test, some of the questions were identical questions from the My Math Lab test review. Like identical, like I didn't even change it, like copy, paste. Okay?
Now you're going to change Mrs. Crystal.
No, I'm not going to, because there's still going to be people that aren't going to bother to look. You think I'm joking? It's the reason I have an ulcer. Just kidding, I don't really have an ulcer that I'm aware of. Anyway, so you guys, we're leaving leaving polynomial land, and we're going to a new place called rational. So this is a new structure, a new type of function. Basically, the structure for rationals is going to be one polynomial divided by another polynomial. And so you might be thinking, why is she writing polynomials? She just said, we're not doing polynomials. Okay, the components and the pieces are polynomials, but the whole entire structure itself that I've created now is a fractional structure. So that's different than what we would see with just a polynomial. In fact, the word ratio right there literally means a ratio of two things. So there you go again, fractional structure. All right. So the minute I introduce this new structure, right, where I've got a denominator again, I hope you guys didn't forget that's going to mean that there's some domain considerations we're going to have to make, right? All right, so and let me just give you a heads up, because otherwise you might feel like particularly lost today. I'm going to give you all this information, and it's not going to make any sense, because I'm not going to give the concrete examples along the way. I tried that in my first class. I just felt like it wasn't going really well. So I changed it for my other classes, and it went much better. So, and I'm going to keep reminding you throughout that as you're writing this down and you're like, I really don't know what she's talking about, it'll all come to clarity later. So I'm like going to have you set up your guidebook first, and then we'll do the examples. So I'm listing all the information you're going to have to be able to do so that you can graph rational functions by hand. Okay, but we already said domain was the first thing. I hope this is not new to anybody, that you should set the denominator equal to 0 and solve in order to find your issues, your domain issues. That statement right there should be a review to you at this point. Actually, that was a test question from the first test. Find the domain of something, and it had a denominator. Now, what is new is last time when we would do that, we would just find the domain issues and be like, those are the bad values, and we would stop. Now we have to progress, okay? Your domain issues that you get can manifest themselves on the graph in two ways, okay? So they can either show themselves as something called a hole or show themselves as something called a vertical asymptote. I'm actually not going to give you formal definitions for vertical and horizontal asymptote. I can, if anybody would like. I'm going to give you my version of how I want you to know it later with an example. So it's going to feel like a little bit of a puzzle today, but then it's all going to hopefully come together. It's worked generally, I think, the last few classes. All right, so there's a couple actual sentences that I want us to write down, but first we're going to find the domain. All right, you're going to get that. That's step one. Then to see how the domain issues actually are going to show themselves on the graph, you're going to factor the numerator now as well, because usually typically at this point you've already factored the denominator, so you'll factor the top. And you're going to try to do some cancellations. Concrete example coming up. Two options. So the first option, the domain issue that you found above, domain issue leaves a hole. It's going to leave a hole if its factor gets canceled, if its factor gets canceled with the numerator. On the other hand, your domain issue could manifest itself as something called a vertical asymptote. That's going to happen. This is going to happen if the factor is still standing after doing your cancellations, or your, I should say, attempts at cancellations. So just to clarify also, basically when you find your domain answers, okay, the answer to the next part, which is the manifestations, is going to be the answers you got to the prior question. All you're doing is taking those and classifying them. All right, so your answers here are going to be the answers here, but you're just going to tell me like which one of the two types it is, because those are your two options. There's nothing else to choose from, okay? And you could have like both, or two of these, or two of those, or one of each. I don't know. It just depends on the function. But once again, concrete example is coming up, so just hold tight with me, and we'll make sense of this. So the next thing they are going to ask you to do to facilitate a nice graphing procedure is they're going to ask you to find any x-intercepts, but you've been doing that for the last like 3 classes or so. And that process is similar with rational functions. For polynomials and quadratics, what we've been doing, was taking the thing and setting it equal to 0 and using whatever methods we possibly could to solve. Well, that process is similar here. What we're going to do is take what's left of the numerator, meaning like after I had done cancellation, and we're going to set that equal to 0 and solve. So it's that same step again. All right? Why numerator and not denominator? Denominator equals 0 is something else. That's the domain problems, right? So that's all. You've already done that. You've already used that up. So then what would be left would be the numerator. And those would give you your x-intercepts. The other thing they will ask you to do is also find a y-intercept. But that rule is not new. You've been doing that with the quadratics and the polynomials.
Yeah, it's back.
Oh. Okay. I have no idea how that happened. Like, no idea. Whatever. Hopefully it doesn't happen again. Okay, so you're going to do f of 0. So that's not new. Okay, it's always f of 0. You want the y-intercept, you always do f of 0. I don't care what the thing is.
Scroll it up.
Oh, yeah, sorry. All right, that time I did that. All right, so that's what was on that line. The y-intercept, you're going to do your f of 0. That one?
The x-intercept.
It's typed in there. Set what's left of the numerator equal to 0 and solve. Yeah. I didn't write anything else. I wanted to leave myself room, but I don't want to say anything else at the moment. I can do more further clarifications later. All right. Okay, well, this is chopped off. What it says is end behavior of rational functions. End behavior. All right, so just like with our polynomials, you guys remember we had to find the end behavior. In other words, how the arms behave, lazy touchdown, swole boy, whatever is that. All right, we got to do the same thing with rationals. But what's going to happen most of the time is different types of behavior. Sometimes they can behave like polynomials. But what we have to consider is a more involved process. All right? There are several options for how your graph, your rational function, can like come from negative infinity and then go on towards positive infinity. All right? your process will be similar to how we did it with the polynomials, in the sense that you are going to go and look at the degree. So what you're going to do is you're going to refer to the original function and locate the degree of the numerator and the denominator. Because remember, degree was part of the puzzle before, right? It was degree and leading coefficient. Well, this time it's degrees and then something different. But it's at least somewhat similar. All right, we have several options. By the way, as I go through this, I know it's going to feel like a lot if you guys haven't seen this before. I do have a mnemonic to tell you later to like really shorten it and make it easy to remember. So just throwing that out there when in 5 minutes you're like, oh boy. Okay, our first situation that we could have is if your numerator degree is less than your denominator degree. So that's one option when you go and you look at each degree. If the numerator degree is less, what you're going to have is something called a horizontal asymptote at y equals 0. That's the answer, period. So what do I mean by vertical and horizontal asymptotes? Okay, I'm going to show you in a moment. Basically, they are like things that guide the behavior of your graph. Okay, I'll give you a little more specifics momentarily. Your other option is when you look at the degree of the top and the degree of the bottom, you could have the numerator degree being equal to the denominator degree. So that would be a situation 2. If the numerator degree is equal to the denominator, then you're going to have a horizontal asymptote located at y equals the ratio of the leading coefficients. All right, usually most students are like, yep, not a clue what that means.
Is the asymptote like where the graph gets close to touch or something?
Yes. Yeah, asymptotes are those things like where the graph gets close, doesn't touch. It depends on which one, but I will clarify, but you're right. All right. This is a somewhat convoluted phrase for doing something that's very simple and straightforward. Concrete example coming up, all right? So just jot it down, and then I'm going to have you keep looking back and reading these things to me so that you know how to read them. Okay, situation 3. If the numerator degree is, hang on. I want to say if the numerator degree is at all greater. At all greater. I don't care if it's greater by 1, greater by 2, greater by 50 million, whatever. If the numerator degree is at all the greater one, okay, then there is no horizontal asymptote, which I will from now on refer to as an HA. In fact, I'll abbreviate all the asymptotes. So like VA will be a vertical asymptote. HA, that's what we're going to do for horizontal asymptote. All right. Now, once we're under condition 3 or situation 3, there is a further fork in the road that we must take. I'm trying to get my words to come back. Every time I scroll, a different part of the sentence disappears. What in the world? Oh, there it is. Okay, I caught it. All right, so under situation 3, we have 2 options, A and B. If the numerator degree, so we're saying in general, if your numerator degree is greater, you're not going to have an HA. But now to be more specific, if it is exactly 1 greater than the denominator degree, then there is something that we will call an oblique. Some books call it a slant asymptote. I'm going to call it oblique asymptote in this class, so I'm going to call it an OA. Huh? Basically, that's just going to be like a diagonal, okay? So if it's not vertical and it's not horizontal, then it must be diagonal. And you actually would find this by doing one of your favorite things from intermediate, your polynomial long division.
That's fun.
That was a joke. And I will go through that process towards the end. On the other hand, if the numerator degree is bigger by 2 or 3 or 4 or more, whatever the case may be, then there is no oblique asymptote. OA, oblique asymptote. All right, what do you think? Clear as mud? Yeah, none of this makes any sense. I know. All right, so that's what the examples are there for. And we're going to go back and we're going to hit all these pieces and try to pull it together. So let's see here. Oh my God, with this piece of junk. All right, whatever. Okay. We'll just have to go with it, because I don't know why it's not reading it. So, okay, this sentence that's chopped off says, all right, now that those are all the things you're going to have to consider, to get an accurate graph, you're going to finish it out by plotting extra points before and after all your x-intercepts and your VAs and holes and stuff like that. What that means is, when it's time to come and do a final graph, I want you to pick extra points to help you, like, connect the dots, literally. Did you ever think connect the dots as a kid would be useful someday? It is, okay, because that's how you graph stuff. You get dots and you connect them. But you want to get them from all the patches of the grid, you don't want to only pick points that are only right here. You want to go before that asymptote, after it, in and around all your features that you have. So that's all that means. All right, so now an example to try to make sense of all the stuff we wrote. All right, here we go. We have a function. This is a Fred. This just says this is an example right here. F of x is equal to that thing. All right, your eventual goal is to graph it, but it's going to ask you to do all the things along the way, and it's all the things we just made a note about. First things first, you're going to take that denominator and set it, technically not equal to 0, because you want to say, I acknowledge that thing is not supposed to be equal to 0. Any ideas on how to solve that? Factor it. Yeah, let's try it. Good.
2 and 3.
Plus 3 minus 2, right? All right, so now I have a product set equal to 0. That's a zero product property, which is why I'm allowed now to take each piece and set it equal, or in this case, not equal to 0, but it's the same idea. Okay, you guys, so what we find is that we've got some problem children here. The x values of -3 and 2 absolutely must be avoided for this function. In fact, the function avoids them on its own. It knows that. So we know that this graph is not defined at those two locations. So those are the answers for your domain. Yes?
I don't understand the not equal stuff.
Okay, basically what you're saying is that when you're finding this, you're trying to say that you acknowledge that this is the value it can't be. You know what I mean? Like if you don't put the or equals to all the way, I'm not going to take off points, but at the very end I need you to put it, because that what you're saying is that this is what I'm specifically avoiding.
So X cannot be.
Can't be those.
X cannot be.
Right. Right. That way when we go to interval notation, that's why those were always like left out with the U's, Okay?
Manifestation. You say manifestation of domain. Is that just the interval notation?
Nope. You could just stop here. Yep. For manifestations of the domain, so manifestation, how does it show itself? How does it materialize in front of you, right? All right, so we're going to go to our notes. I want somebody literally in the room, please, to read the line under manifestations of the domain, my typed line. Go.
To see how these domains issues affect the graph, factors numerator now as well, and cancel common factors.
So those things, those domain issues are going to show themselves on the graph in a number of ways. First thing we're going to do is we're going to shimmy back up to the top and we're going to factor the numerator now as well. Well, the numerator is already factored. There's no factoring to do. It's just x plus 3. That's as good as it's going to get. And I just like to jot this back up towards the top for organization's sake. I'm going to factor and I'm going to attempt to do some cancellation if there's any cancellations that can be done. Is there any cancellation that can be done?
Yes.
Yes, I see a factor of what?
X plus 3.
Okay, x plus 3 and x plus 3, those are going to go away, right? So could somebody please now read what we wrote for holes? Anybody, don't be shy.
Only if its factor gets canceled with the numerator.
All right, so my domain issue is going to leave a hole in the graph only if its factor got canceled with the numerator. Okay, so look, this little problem child, negative 3, he came from the factor of x plus 3, right? Yes, say yes.
Yes.
That's where he came from, okay? So when I'm going and I'm looking at how this thing is going to show itself on the graph, I can see that if I were to factor it out, that actually would get canceled out. So what happens is we actually have a hole located at that area. So if it cancels out with the numerator, you're going to have a hole in that spot. Think of it like this. Think of it like an equal and opposite like punch out, right? X plus 3 in the top and x plus 3 in the bottom. They knock each other out. This thing isn't strong enough to bend the graph. It just you punched a hole out of it right there. Okay?
Is that the mathematical way of writing?
That's my mathematical way of saying it. Well, yeah, it actually is the way. That's the reason. Mm-hmm. Yeah, okay. Now, my other option, somebody read me vertical asymptote. Oh, question, go ahead. Oh, that bottom, you know, we did it right here, so I was just copying it over in its factored form. Right. Does that make... Right. Yeah, the negative 3, you know, comes from the x plus 3 factor. If you guys go on to pre-cal, that's like a huge thing you need to remember, that the roots or whatever, or the answers to the, when you set things equal to 0, is always the opposite of the sign in the factor, you know. You've probably picked up on that, but... Okay, somebody want to read vertical asymptote for me?
The factor is still standing after cancellation.
So you guys check this out. When I did that cancellation, my Fred, feasibly we could think of it as like being reduced to like 1 over x minus 2, right? Because the x plus 3's went away. All right, so would you guys agree that after my attempt at cancellation, would you guys agree that the x minus 2 is still standing? Nobody canceled him out. All right, that is what produced this guy. You can see right here, that's where he came from. So if it's still standing after cancellation, it's strong enough, it withstood the cancellation, okay? It's got enough clout to actually bend the graph, okay? So what's going to happen there is you're going to have a vertical asymptote at the location of x equals 2. So, and please notice, what did I do? I got my 2 domain restrictions. All I do in the next one is classify how they are. You know what I mean? Like I'm copying the answers down. So negative 3 should be in this answer again, and 2 should be in this answer again. If a factor cancels out and it's not still standing after it punched a hole, if it's still standing, it's a vertical asymptote. That's it. Those are your options. No, there's no other options.
What about the oblique?
You'll see.
Okay.
Yeah, and you know, like right now I realize that like this also still means nothing until I get to the picture, so contextual example coming right up. Give me like 10 more minutes and we'll get there. All right, now you have to find the x-intercepts of this thing, if there are any. Would somebody please read out loud? What's the thing for the x-intercept? Go.
See what's left of the numerator equal to 0 and solve.
All right, take what's left of the numerator. So I had my friend, I did my cancellation business. Would you all agree that 1 is what's left of the numerator? Does that make sense? Okay. See, I tried to like say it in English. So like,
Well, 1 can't equal 0.
okay, right. So if I follow the directions, I'm like, okay, she said set what's left of it equal to 0 and try to solve. Okay. 1 equals 0. No, it doesn't. Okay. So look, I try to solve. First of all, that's a false statement. That doesn't even make any sense. So there's no variable here for me to solve for. So I'm trying, but I'm not getting anything. So what this means is that this graph, what do you think?
Has no x-intercepts?
Has no x-intercepts, which is totally possible. Is that what you were going to say?
Well, I was going to ask, in the event that the x plus 3 was still standing up there, it would have been x plus 3 equals 0, and
Exactly.
then the x-intercept would have been negative 3.
So if the x plus 3 was still standing in the numerator and it wasn't a domain restriction, then it would be an x-intercept. Yeah. But I have another example coming up where we're going to do like all the alternative options, so you'll see each of them. So if you're like, well, wait, what if it was like this? It's coming.
Oh, sorry.
So every time the numerator cancels out, we can pretty much assume there's no x-intercepts? Like the whole numerator cancels
Yeah, like if the numerator like cancels down to just a number, you know, where there's no variable that you can solve for it, then yeah, you know there's no x-intercept, because when you try to set it equals 0 and solve, there's nothing to solve for. Yes?
So if the x-intercept is the exception, it's just a false statement, and it's just knowing your x-intercept. Oh.
Well, we're trying to see if there is one, and that is the process by which we would do it. But so there's not one, because I can't fulfill that process. Right. Okay, so then the next thing we got to do, you guys, we got to find the, yeah, that's what this says right here, so I apologize for this stupid computer. It says find the y-intercept if there is any. Well, remember, that's going to be the same thing every time. You're always going to do f of 0. So,
Oh, the factor form, or just like the original?
okay, so actually you can use either one, but I'm going to just encourage you to always go back to the original f, and the reason I'm going to do that is because that way we're just doing the same thing every time and it stays consistent, okay? I want things to stay consistent. So, to find the y-intercept, I'm going to go back and stick a 0 in wherever I see an x to my Fred. So it's going to look like this. 0 going in everywhere that I see an x. Okay. The cool thing is that all those little 0 pieces, you know, they're zeros. Okay, so they're not even there, right? You know, so you're going to like negotiate the constants. So what I'm saying is, some of you don't even have to write this. When you all realize that you stick a 0 in for x, that all those x terms disappear, you're just left negotiating the two numbers, right? Am I making sense? Okay. Okay, well, that can be reduced, by the way, so we should do that. So negative 1/2, okay, that's going to be our y-intercept. Okay, identify the end behavior. All right, this is where we need to go back and consult that ridiculously long 3-situation thing, but I do have something to help you. So before we do it, I'm going to go back. I'm going to go back to, this is the first page of the notes. Here's the mnemonic for remembering. Situations 1, 2, and 3. And I can't take credit for this. A student taught me this. You're going to do the laser gun. L-Z-E-R-G-N. Check this out, check this out, check this out. Okay, here's how it works. Situation 1, situation 2, and situation 3. You're always comparing the numerator to the denominator degree. The numerator degree to the denominator degree. So you're going to ask yourself, is my numerator degree, how does it compare, to the denominator? If it is less than the denominator degree, you're going to have a horizontal asymptote at y equals 0. Less 0. If the numerator degree is equal to the denominator degree, then you're going to have an asymptote at y equals the ratio of the leading coefficients, which I'm aware that still probably doesn't make any sense, but we'll cover that example in a minute. On the other hand, if your numerator degree is greater, so if the top degree is greater than the bottom, you're going to have no horizontal asymptote. And by the way, if you're going to calculus, your first chapter is going to be about limits, and there's a specific section about how you figure out limits as x goes to infinity. That is all you need to know. It's nothing but the horizontal asymptotes all over again. The minute you know that whole section of calculus is like, oh, I already know it. Okay, so now that I gave you a mnemonic, let's see if we can figure it out. So let's identify the end behavior. All right, our notes say that in order to do that, I need to go and look at the degree of the top and the bottom and go from there. You guys, what is the degree in the numerator? 1, right? X to the 1 is the highest thing, right? What's the degree of the denominator? 2. So you say the degree of the numerator is less than the degree of the denominator. So you don't even have any math to do. You just say, okay, I know automatically that means I'm going to have a horizontal asymptote at y equals 0. Less is 0. Numerator degree is less, so that's a situation 1. So if you look at your situation 1, bullet number 1, then you're going to have an HA here.
Why isn't it plus? It's exactly 1.
One greater than the bottom.
Yeah.
But that's the
No. I'm saying if the numerator is 1 greater. No, this is less. Yeah. Okay, so here's what we need to do. I need to go graph this, which means I have to get away from everything I've written, but you guys have it written, so you're going to have to help me, all right? Because I got to scroll and I can't see what it says. So what's going to happen now is hopefully we're going to really be able to make sense of everything that we've calculated, and written. All right, so back up to the top. We had our domain restrictions. There's nothing I really draw for those just yet until I go to the second part, which is vertical asymptotes and holes. All right, you're going to start with your vertical asymptote. So I had a vertical asymptote where? It was 2, right?
2, yeah.
So I want you to draw a vertical, dashed line on your graph like this. Yes?
So there is no OA?
Yeah, no, there's no OA.
There is an OA, just not here.
Not in this function. All of those, okay, so listen, all of those situations are mutually exclusive. Like if you're a 1, you cannot be a 2 or a 3 or either subset of a 3. You know what I mean? Yeah. All right. Now listen, you guys, this is not a part of the graph. I know that sounds weird. This is not a part of the actual graph. What I had you do was set up and show this is the line that's going to basically cause your graph to bend and avoid, because that is a domain restriction. This is specifically where the graph is not. That's what a domain restriction is, right? So, but here, I want you to write this down. So I want you to write that this is a vertical asymptote, okay? This, you guys, is like a double yellow Like on the roads when you drive, you're not supposed to like cross a double yellow. Okay? But like in Tampa, no, some people don't know that. So, yeah, you're not supposed to cross a double yellow if you didn't know. You will probably die. Okay? So we're drawing it because it's going to end up guiding our graph. And I do want you to draw it, but realize it's not a part of Fred. This is showing where Fred is specifically not going to be. All right, did we have any x-intercepts and y-intercepts we could jot on here to help us? No x-intercept, and there was a y-intercept. -1/2, great. End behavior. That was the horizontal asymptote. Where was that? Okay, well, y equals 0, you guys, is right here. Right on the, right on the x-axis like that. That is also a guideline. So if you're like, you just said you can't cross the VA and you just crossed it. No, I didn't. These are like road markings, okay? My actual graph that I'm about to draw for you itself will never cross the VA. So you're probably wondering, well, what about HA? What is that? What does that do, or what is it like? You guys, in HA, this is like the dashed white lines on the road. Like when you're driving down I-75, in your lanes, there's like dashed white. You can cross them if you want, but generally we just follow them, because if you don't, then it's scary.
Wait, I thought the graph never crosses the horizontal asymptote.
No, it can. It can. So in the same way that you're never supposed to cross a double yellow, the graph is never going to cross a VA, ever, ever. It is a domain error there. You can cross an HA. Generally, they surf it. The graph will surf it, but they are crossable. Not all the time will they cross, but they can if they feel like it. All right. So now it's time to graph by doing, plotting extra points. And this is why you have a graphing calculator in this class. I am not going to plug in a bunch of million zillion different points because one stinking dot is not enough for me to graph this thing. Do you know what the graph looks like from this alone? No.
Yes.
So go to your calculator. Go with me to your calculator, and I want you to punch in. Go to your y equals. All right, we're going to punch in this Fred so that we can get extra points to plot. Now, granted, when I'm plugging him in, if I hit graph, I'm going to get straight to the answer for this whole question anyway. And that's fine. I want you guys to be able to look at the answer. So remember to put your numerator and denominator in parentheses, right? So look, if I were to hit graph, there you go. There's the answer. That's what your graph is going to end up looking like. All right, but you wouldn't know that because you haven't seen these before. And that's why I always say we're going to plot some extra points, and we're going to play a game of connect the dots. So the point of coming here is to go to our table, and let's select some dots from all over the span of this grid here so that I can make sure I've got a clue about how this thing is going to wiggle, okay? You guys, some of you have this plugged in for me, yes?
Yes.
So then you can give me some dots.
1, -1.
Okay, thank you. That's perfect. Okay, so we've got, someone tested a 1, so we've got a 1, -1. Ooh, that's a dot. So give me a few more maybe in this area. How about,
You got -2, -2 on the x, and then the y is -1/4.
okay,
A clean one would be -8. No, that's not clean. I lied to you. There's no clean ones.
not really. Hey, what do you get when you plug in a -3?
Error.
Ah, that's because there's a hole there. Should be an error. What about -4? I know it's ugly.
-1.667.
So let's just say roughly -0.2-ish.
So how would you draw the hole if you don't know? You just drew the open circle?
Yeah, so here's what we do. Do you guys see how it's starting to go like this? Okay, that's what a VA does to your graph. Remember we talked about that with the reciprocal function? Like, you know, when it gets close to it, it knows it can't touch it, so it's like, right? So it's going to do that, and you can see that happening. So with just a few points, you can be like, okay, that makes sense. It's not supposed to touch that thing. So that, like, arm goes like that. And you could test 50 dots over here if you need to be really sure. Now what you're going to do, though, is be very careful. At your x value of -3, at the x value of -3, you want to make sure that you put a hole there. Because that's literally what happened to this graph. There is like a chop. Like someone came in and took a piece of scissors and chopped. And there's a little gaping hole at the actual value of -3. How about some dots on the right?
We got 3, 1.
Okay, 3, 1. How about 4?
4 and a half. Yeah,
4, 1/2. All right. Now, because you have the calculator to assist you, which is what I want, you know, once you get a couple of those, that's usually enough to help you realize that your arms are going to bend like that on that piece of the graph. So here's what you should be seeing. You should be seeing your graph going out of its way to not touch your vertical asymptote. Double yellow. If you draw me a graph in which you cross right over the vertical asymptote you just wrote, I will have a fit. Okay?